Good afternoon, everybody. We are very pleased to have Dr. Debashree Ghosh from ISCS Kolkata as an institute speaker today. Just to briefly introduce Debashree, she obtained her BSc from Presidency College, now University, in chemistry major in 2002. Subsequently, she obtained a master's from ISC Bangalore in 2005. And then she obtained her dual degree of MS and PhD from Cornell University in 2009, I think. And then she moved to the University of Southern California, and where she did her postdoctoral work since 2009 to 2012. Then she came back to India and joined the National CSR, the National Chemical Laboratory, NCL Pune, where she has worked as a senior scientist since 2012 to 2017. And then she moved to ISCS Kolkata, where she is an associate professor in the School of Chemical Sciences. So the major research interest of Debashree lies on the electronic structure theory, quantum chemistry, and of strongly correlated system. And she has obtained various awards, and among them, the most important one is the annual medal of the International Academy of Quantum Molecular Sciences, which she has obtained in 2012, and only a very few Indians are recipient of that prestigious medal. So with that, I request Debashree to kindly start our talk. Debashree.
Thank you so much. Thank you for the very kind introduction, and thank you for inviting me to present our work. Let me share my presentation. My screen is visible?
Yes, it is visible. Just make it full screen.
Okay.
Yes, perfect.
Okay, so good afternoon, everybody. Today we are going to talk about solving the quantum chemical Hamiltonian in strongly correlated systems, and we will see how we can move from a variational approach to the machine learning approaches, and what are the problems associated, what are the benefits, and so on. And just to give a kind of introduction of what we do in our group, we are a quantum chemistry group, and we are interested in excited states of biological systems. To attain that goal, we basically develop hybrid QMMM methods. And since the name hybrid QMMM is there, so in that context, we have to develop fragment-based and machine learning-based polarizable force fields as the MM. And for QM systems, we develop strongly correlated methods that can deal with strongly correlated systems. And once we have developed these methods, we kind of like to apply them to our pet projects. One of them happens to be photoprotection in melanin, and the other spectroscopic properties of fluorescent proteins, RNA, etc. And today we are mostly going to talk about this part of strong correlation and tensor product states. So as an anchor to understand the need for these new methods, let's start with the system of the acenes. And we are interested in calculating the singlet triplet gap of acenes because that's important in energy processes such as singlet fission. And although the system looks fairly simple, there's nothing other than carbons and hydrogens. It so happens that in 2004, DFT predicted that there was a singlet triplet crossover, which means that as we increase the size of the system, as in we go from, let's say, tetracene to pentacene to hexacene, so on and so forth, the triplet state becomes more stable than the singlet state. This was predicted by DFT. However, in 2007, it was predicted that no, there is no such crossover. And the reason that there isn't such crossover is because there's a major effect of static correlation. In 2010, it was already, at that point, it was already experimentally known that there's no such crossover. But CCST parenthesis T calculations showed that while there was no crossover, the reason for it was a dynamic correlation. And in 2015, our group showed that both static and dynamic correlation and a balance between them is required to understand the singlet triplet gaps in these molecules. So even those innocuous looking molecules seem to be doing something devious over here. Let us see another example of strong correlation in chemistry, which kind of illustrates the point even more. So we take a very small molecule, water, and pull its bonds apart. So increase the OH bonds. And once we do that, we can plot the energy with respect to the bond length. So the black curve is the exact result that you would expect. In fact, that's what you would expect, right? The energy goes smoothly to some energy of which basically some dissociated energy. There shouldn't be humps and bumps and things like that along the way. However, normal single reference methods such as MP2, CCSD, and of course, our favorite DFT shows these kind of strange behavior. And in fact, if we plot the errors, that's even more disastrous because the error goes to infinity as we pull the bond apart. And since I am a chemist, so I need to break and make bonds. And if this is a signature, problem that happens in the single reference methods, then I'm in trouble. And also this strong correlation, this effect of strong correlation shows up in excited states, in diradicals, triradicals, transition metal complexes, polyenes, you name it. And in this talk, I will allude to the excited states and the polyenes, graphenes, those kind of systems. So why is it that this is happening? The reason for that is there are two different forces that are acting in these molecules. So the electrons, they will try to delocalize and take up as much space as possible, but this isn't just one electron. All of the electrons are everywhere and they would try to avoid each other. So there's this kind of two different forces that are acting. And another way to look at it would be from the chemist's picture of orbitals. You know, we like our orbitals. So if, let's say, we have these orbitals and as is normally done, we would populate from the lowest energy orbital up to the highest occupied molecular orbital, and from everything from the LUMO onwards, higher energy ones, would be empty. That's what you would expect. And there would be some gap between the HOMO-LUMO, and that will predict many of the properties of these molecules. But what happens when this delta E, the HOMO-LUMO gap, is quite small? In fact, in that case, you cannot consider just one of the molecular orbital pictures or one of these configurations as the predominant configuration. And therefore, you have to basically take all possible combinations which are reasonable in energy, which are reasonable in importance, and we have to kind of shift from the single reference picture to a multi-reference or multi-configuration picture. So you might say that, okay, what's the problem? We will take a multi-reference picture. How many references can there be? So let's see how many references there can be. So let's again look at the system that I alluded to before, the acenes. Here, the active space or the valence space should contain all the pz orbitals. So basically all the pi and the pi star orbitals. So if I have 30 such pi orbitals and 30 such electrons in them, which basically translates to 30 carbon atoms, not that big of a molecule, the number of configurations one has to consider is 10 to the power 33. That's a huge number. Let me put that in perspective. For a matrix diagonalization of this size, essentially one requires to perform a 10 to the power 99 operations. And our universe and the total number of atoms in this universe is only 10 to the power 82. So no matter how big of a computer I am provided, I will never be able to solve this brute force. So I have to basically think of some tricks along the way. And a nice way to look at why this scaling, why this number is blowing up so quickly is from this example of spin states. So let's say I have sites. These three are sites, and on each of those sites there are spins. So the spin can either be up spin or down spin. So if I have three of those sites, essentially I'll have all of these different types of combinations of spins that are possible, which basically means that I have 2 cubed spins. So if I have n such sites, essentially it will become 2 to the power n such possibilities. Now, whenever the n is in the exponent, the size is in the exponent, I'm in trouble. That's exponential scaling. So if instead of a spin, I had some other quantity, let's say the orbital occupancy or something like that, it would be d to the power n, depending on how many configurations are possible per site. Okay, so how do I, in this picture, how would I write the exact wave function? Essentially, this is what it would look like. So this beast over here is a 2 to the power n dimensional object, which has each of these dimensions shown as these pegs of a ladder, kind of. So this is essentially a matrix product state way of looking at things. And let me explain matrix product states a little bit so that I can talk in that language later on. So essentially in that picture, a real number would be represented as a circle or something with no ladder sticking out. A vector, since it has one dimension, it would have one ladder which is sticking out, one peg which is sticking out. A matrix would have two such, and a tensor of, let's say, 5 dimensions will have 5 such things sticking out. And notice that I have dropped this index along the way because that's how you go. That, I'm trying to have this pictorial notation so that writing the equations can become easier, so that I have the minimum amount of bookkeeping to do. That's why I'm not even writing the indices like that, because I'll run out of alphabets maybe. Okay, so if I were doing in this notation, if I were doing a matrix vector multiplication, a matrix would be something with 2 hands, and a vector would be something with 1 hand, and you would be contracting over this common index or the common hand, which is the j. So this is the contraction operator, which pictorially would look just like this, which is a much simpler notation than this, especially when you have many such i's and j's and k's and everything flying over the place. Similarly, if you were trying to do the trace of some product of matrices, this is what it would look like. So there's nothing sticking out. Trace is a number at the end, so there's nothing sticking out. And you can very easily keep track of how many indices I'm left with, what is the rank of that matrix of that tensor, and things like that. And therefore, in this matrix product ansatz, as I have shown before, since there are n different or k different dimensions in k over here, so in k different dimensions, they are denoted by these ladders or things that are sticking out. And now if I take this huge object, which as I saw was going to kill me because it scales to the d to the power n. So if I perform a singular value decomposition, how would I go about doing a singular value decomposition? So I can think of this index as an index and the rest of the indices as a combined index. I am allowed to do that. There is no problem. And therefore, I can do a singular value decomposition along here. If I perform that, this is exactly what it would look like. This would be a matrix with 2 legs. This would be also a matrix, but notice I have drawn it in a different way than here, because this is a diagonal matrix, because I have done a singular value decomposition. And the rest is a object that I'm left with, the rest of the indices. And if I just put this diagonal matrix and multiply with this one, I essentially can have just one site index, one object, one matrix, which depends on one site. And I keep doing this ad nauseum. Again, I cut over here, and keep doing that. Then I'll end up with something that looks like a product of tensors or product of matrices. So first one is a matrix, second one is a tensor of rank 3, and so on. So this can indeed be a good representation of this one. And in fact, let's look at the number of degrees of freedom that this object over here has. This also looks kind of complicated, right? So if I see there are n of these objects, because d to the power n, so there are n of these circles, and each of these circles, except the ones in the corner, are of the dimension m times d. So d times m squared. So this is the total scaling of this object now, which is a huge saving from this d to the power n, because essentially it's an exponential saving. I've started with an exponential object and have made it into a polynomial one, which is fantastic. So if I write out the wave function in this notation, this is what it would look like in the ugly, algebra notation. That is why we don't like to write out in these algebraic notations, rather have it in this pictorial forms. Okay, so how would I get these matrices? That's where, in fact, the algorithm called density matrix renormalization group comes into picture. As I mentioned before, this was this spin system, 3 of the spin systems giving rise to 8 possibilities. Of course, if there are more and more of those spin sites, I'm going to be headed in a very wrong direction very quickly. But what if I took all possible combinations of just 2 of these sites? That's always going to be 4. That's not too many. If after I look at these 4-dimensional object and calculate its density matrix and retain only those states which have the highest diagonal value of those density matrix, which essentially means the most important of these states. If I retain only 2 of them, and then I again increase the degree of freedom by taking all possible combinations with the next site. Again, I increase the degree of freedom, and again look at the physics of the system and reduce the degree of freedom. So by these successive steps of reduction and increase and reduction and increase and so on, I can take care of a whole long a train of these spin sites, and still I'll be able to take care of the physics of the system. So that's basically, that's how I will get the matrix product state answers for this system. In fact, if I were thinking of not the spin states, but the orbital states, because that's what I'm going to be looking at the chemical systems, so therefore orbitals, this is what the wave function, the full CI, the exact monstrous wave function will look like. And each of the sites n will have 4 possibilities. Each of the orbitals can have no electrons, can have 1 up electron, 1 down electron, or 2 electrons. So there are 4 possibilities, and therefore if I had n such sites, there would be, or orbitals, there would be 4 to the power n scaling. In the mean field approximation that we all love, which is essentially Hartree-Fock, or in a different way DFT, you basically have product of these objects. You basically you kind of approximate this monster into just products, and because these are just products, of course anti-symmetrized, you don't have the correlation between site to site. On the other hand, if I introduce some amount of correlation between adjacent sites, I can take care of the strong correlation to quite a large extent, and therefore I would end up with a product of matrices, which is nothing other than the matrix product state that I talked about before. So DMRG gives us a good algorithm to determine these matrix product states. And it is quite economical as long as each of these matrices or tensors are not huge in dimension. So essentially this, if I go back, this D is the dimension of each site, but as long as this M states, the number of states that I need to retain does not become too large, this is in fact a very economical algorithm. Okay, so using DMRG, it has been shown for these polyacenes that as you increase the size of the polyacenes, the polyradical, first the biradical nature and then the polyradical nature of the ground state increases. So basically the multi-reference nature of these systems increases as you increase the size, which is shown over here. This was done in an earlier paper by Garnett-Chan. And we have also shown that using a whole group of multi-reference methods, you can get the singlet triplet gap quite accurately with respect to length of acenes. And here we have indeed compared with experiments. Okay, so now let's get a little bit more adventurous and try out a little bit modifications on these systems. So instead of simple polyacenes, we also look at azulenes. And we know from our BSc chemistry that the singlet triplet gap of azulene is much lower than that of naphthalene. And the reason we say is because there's some charge transfer in order to retain the aromaticity and things like that. But at the end of the day, here you can see that you can indeed show this change in singlet triplet gap using whatever levels of theory you choose to use, as long as you incorporate the multi-reference elements into them. So what we have done is created a few different motifs of polyaromatic hydrocarbons. Polyacenes were, of course, studied quite a lot before us. Polyazulenes were just starting to get studied, and these fused acene azulenes. So now if I compute the singlet triplet gap, this is what we get for polyacenes, again, known before us. In case of the polyazulenes, although it starts much lower than the naphthalene, but the slope of it is much higher, slope of it is much lower too. So it doesn't go down to very small singlet triplet gaps as we wanted it to. We do not get any singlet triplet crossover anytime soon. On the other hand, if we take these fused acene azulenes, these can give rise to a huge reduction in singlet triplet gap. And in fact, this is the 0 over here. So there's a singlet triplet crossover within system size 5 or 6 rings, which is actually tiny molecules. So this makes it much easier to synthesize these molecules and actually see the singlet triplet crossover. So that's all great. That the fused acene azulene systems that we proposed have a very low singlet triplet gap and a singlet triplet crossover. But why? So what was done before us, whenever people saw these changes in singlet triplet gap, they kind of tried to correlate it with diradical nature, as I showed in that Chan paper earlier. So we went ahead and did that. This is a plot of the singlet triplet gap versus occupation number of the LUMO, which is a good measure of how much diradical character these molecules have. So you see this graph does not show any correlation whatsoever. So in fact, there's something more that is going on. And in fact, the moment that we saw this data, this lack of correlation, we went back and try to think from an orbital picture. Being chemists, we do like our orbital pictures. So let's say I have a system which has some homolumo gap, and therefore this is the singlet state, this is the triplet state. It's the energy difference between these two states that I care about. So if the homolumo gap reduces, essentially the singlet triplet gap should reduce. But in the same breath, we can also see, because of this reduction in homolumo gap, the diradical nature also should increase because this gap has closed down. So essentially what is happening is this orbital picture is completely breaking down, and we cannot explain any of the results of these different polyaromatic hydrocarbons using the mean field approximation that we are tempted to do. So at that point, I kind of came across this paper by Ramshesha and co-workers. And what they had done was looked at quantum phases on frustrated two-leg ladders which are skewed. So basically, this is like a ladder which is skewed. And we could see that this is connection-wise or topologically, these are very similar to the molecules we are talking about. So this is the 7-membered ring, and this is the 7-membered ring, 5-membered ring, and the 5-membered ring, and so on. So some of the qualitative understanding from these ladder systems might be relevant in our molecules. But how do we actually figure out which is more important and which is not for the molecular systems? So in order to, first let me just, maybe in this audience I don't need to, but let me just explain what is spin frustration. Essentially, if I have a spin system where the spins want to be oppositely facing, as in they're antiferromagnetically coupled, then if I have a triangular lattice and I put the two spins here and here, they will be very happily opposing spin to each other, but the third position will not know what to do. It will be perennially frustrated, and that's spin frustration. The same kind of thing would happen if it's a non-collinear spin system. So in order to look at the effect of only spin frustration and nothing else, we removed all the lattice degrees of freedom from our molecule and all the details of the molecular Hamiltonian. So we basically took a very simple model Hamiltonian, which is this Heisenberg model. And in that, we took same J for all bonded pairs, as in all nearest neighbor, which are bonded to each other, they will have a J interaction between them, which is forcing the spins to be opposite. And they are antiferromagnetically coupled. That's all that we incorporated into this model. And we saw, because we fitted this one with the acenes, we saw very good agreement with acene. But what we saw is azulines show some of the correct trends. It shows that there is a reduction in singlet triplet gap. It also shows that the slope of, as in the reduction in singlet triplet gap of the polyazulines is lower than that of polyacenes. Furthermore, we also saw that there was a sharp decrease in the fused acene azulines. So we believe that even in these simple model Hamiltonians, there is something which is qualitatively quite close to what is happening in the complicated molecular Hamiltonians. And since we were at that point looking at model Hamiltonians, that gives us the freedom to really look at each of the configurations, which would be quite difficult in a molecular Hamiltonian. So we saw that the most important configurations of polyacenes, whereas you expect that there are upspins and downspins adjacent to each other, and so everybody is kind of happy with each other in that they are antiferromagnetic with each other. However, when we look at the polyazulines, we see that there are these common same spins that are kind of coming and coalescing in some of the common bonds. So not all of the common bonds. This one does not have those same spin accumulating, but this one and this one has the same spin accumulating. Same thing we see in case of fused acene azulines, only here we see that there are more number of common bonds that are being populated by same spins. So that's essentially, these are the interactions that's destabilizing the singlet state. And because of that destabilization, you have a singlet triplet gap becoming much smaller. So that's what we see from the model Hamiltonians. But you know, model Hamiltonians are still a huge simplification from the molecular Hamiltonian. So how do we know that these effects are really that important in the molecular Hamiltonians? So we went ahead and looked at signatures of these effects in the molecular systems. And we indeed saw those in the geometries of the singlet state. So the singlet state geometry of the polyacenes were known much before us. And in fact, there is this bond length alternation. So basically, you'll have a long bond and a short bond, and then again another long bond, and so on. So you have this nice pattern. On the other hand, if you look at the if you look at the polyazulines, you see that only in those common bonds where the same spin came and accumulated, those bonds were getting elongated. They were in fact getting so much elongated that they are almost like single bonds. A single bond is 1.54 angstrom. This is almost like a single bond. So there's these bonds are kind of coming out of the conjugation pattern completely. And similarly, in the fused acene azulines, exactly where we saw the common spins come and coalesce, in those places we see that the bonds have elongated quite a lot again. So in fact, what we see in the model Hamiltonians, we do notice as signatures in the molecular Hamiltonians also. Okay, great. But again, we have proposed some molecules theoretically. How good are our proposals, in the sense that are these molecules even synthesizable? So we looked at this reaction and calculated the stabilization energy per pi electron. And we see that, so this is a benzene system. It has a 12 kcal per mole stabilization. You see that the systems we have proposed, they are not that far away from the stable already synthesized situations such as azulene, such as a different combination of fused acene azulines and so on. The red ones are the stuff that has already been synthesized, and the ones we had predicted are these. So as far as stability goes, they are not that unstable. They are not expected to be that unstable. Okay, so we seem to have proposed some reasonable molecules, and we have also given some design principles of how to tune the singlet triplet gap using these model Hamiltonians, because these model Hamiltonian calculations are much faster than the molecular Hamiltonian ones, of course. But it is around this time that we got quite a bit more ambitious and tried to extend our understanding to two-dimensional systems. And what these polyaromatic hydrocarbons give us is a nice platform, to try out different motifs, different systems, because all we have is carbon and hydrogen, and we can arrange them in many different forms and look at the properties of these systems. So can we use DMRG-like calculations for these two-dimensional systems? So it turns out that we cannot. And the reason is in fact known. So basically, there's an area law for gapped transitions. So essentially, if you are looking at one-dimensional system, wherever you cut those, because remember, if you are going to create those matrix product states or any of those product state-like things, you will need to truncate your system into two places. I mean, system A and system B. And if you cut along one of these bonds, they remain the same wherever you cut. But on the other hand, if you have a two-dimensional system, if you cut across here, you see that depending on how your system size grows, it will grow in the x-axis and the y-axis and the x-axis. So essentially, your entanglement will keep growing, or rather the entanglement entropy keeps growing according to the area of the boundary. And therefore, you will see that all the algorithms that have been developed for two-dimensional systems in a renormalization group framework, they don't really work that great. The only way is kind of to snake your way through like this. And if you snake your way through like this, what happens is, see, you are taking the entanglement of 1 and 2, and then 2 and 3, and so on. So 1 and 10 is incorporated in a very minimal way. So it will come back, and then you incorporate the effect of 1 and 10 entanglement. But 1 and 10 is just as entangled as 1 and 2. So you are essentially doing a big disservice to that 110 kind of entanglement that you are not considering. On the other hand, if you went like this, 1 and 2 would have the same bad fate. So that basically, there's no way out for these two-dimensional systems. However, it is around this time that I came across this really nice paper in 2017 that the tensor product states, and I did show that the full Hamiltonian, the full wave function is a tensor product state. They can be approximated as a kind of a neural network called the restricted Boltzmann machine. So let me give a brief introduction of what a neural network is. Essentially, if I have some kind of inputs, and or the input could be a direct input or a function of some kind of an input. I will give you an example. Let's say it could be the position of each particle. It could be the spin at each of the sides, and so on. Then you can basically multiply that vector of those inputs with a matrix. So after this matrix vector multiplication, you have what is called a hidden layer, and you can have multiple of these hidden layers. And after quite a few of those, you finally have the output, which is essentially your desired output. So you train your output as a function of input, and the function looks at as like over here, and you are basically tuning all of these parameters of these matrices that are in between. So that's what neural network gives you. It gives you a very flexible framework to approximate a function which may be too complicated to put down as an analytical form. So, but on the other hand, you also see that it is nothing but a matrix vector, matrix multiplication kind of a thing, which is what matrix product states are. So we see a 1:1 correlation between these matrix product states and the artificial neural network. In fact, the artificial neural network, as I have kind of turned it around and written, if it looks like this and the phi x are the inputs and the final output f of x is just a matrix multiplied by a vector of the phi x, this is nothing but this object. And this object is the full CI wave function. So we should be able to approximate the full CI wave function as a machine learning problem, as a machine learning problem which maps into a neural network. And again, what is a machine learning? So let's say my function that I want to find out, which is essentially what is the energy given some configuration, or what is the relative weight given some configuration, if that function is not known and I kind of approximate it as a related function f of x. So how is it related function? This f of x doesn't really have to be anything like this y of x, except that f of x is extremely flexible, which is what neural networks are. And f, the value of f, is close to y for all the training data. So at this point, you might ask, what is the data? We'll see soon. And we are always trying to target for the simplest form of f of x. Why? Because otherwise, see, I can fit an elephant with anything if I have too many parameters. But that's not what I want. I want to give minimum number of parameters, simplest form of the function, and still be able to get this mapping of what is the most optimal f of x. That is essentially machine learning problem, and more specifically, supervised machine learning problem. So if I put our problem as a machine learning, if I kind of rephrase our problem as a machine learning problem, I will write my f of x as this tensor many dimensional object multiplied by the phi's. And in our case, we have taken the phi's as just the spins at each side. So instead of minimizing the energy with respect to this w, what my problem has kind of boiled down to is we optimize W to mimic the data. Now, what is the data? Well, let's say we have some way of knowing the relative importance of some of the configurations. So I have these very many number of configurations. I cannot find the weights of all these configurations because it is too hard computationally. But I might be able to get an idea about a small sample of it from Monte Carlo or methods like that. So that is going to provide us with the data. Once we know that data, we'll just try to find the best possible f of x, which in this case is finding the best possible w that will mimic that data. So now, instead of having a variational problem, we will just minimize this cost function. This cost function is the distance between whatever f of x we have chosen and the exact data w of y of x. And what we are changing in order to get this cost function to go down is changing the w, which are the tuning parameters. So what is the benefit? I mean, I'm just rephrasing one problem as another problem. What am I gaining from that? Essentially, we don't have to compute the energy. See, these matrices, if I do a matrix multiplication in order to get the matrix product operators. So for the operators, I'll at least have to be able to do a norm of the matrix products. And also I'll have to take the Hamiltonian operator in between and calculate those operators actually. So that's actually a much more computationally expensive step than just writing out the W. Just as I showed before, if I had 10 to the power 33 number of instances, the computational cost or number of steps to diagonalize it, which is what would be computing energy, is 10 to the power 99. So it's n cubed time. So that's again more cost than I would like to give. So that is the benefit of rephrasing this problem into a machine learning problem as opposed to a variational problem. Now, let's see our network construction. This is what our neural network looks like. It is not a restricted Boltzmann machine. It's a very simple, normal neural network. So these are the equations that would go into it. And at each of the sites, each of the hidden sites, we incorporate some degree of nonlinearity by using a ReLU function. That is what we have chosen. We have tried quite a few different instances, and this is what gave the best results. That's why we chose this. So this final result is essentially used to model our psi j, which is the relative importance of each of the configurations given here. So if I look at the number of parameters, this is where the huge saving comes from. If I look at the number of parameters, this is it, because each of these things are essentially matrices. Matrices means it has a n squared scaling. So this is a n into n minus 1, because different layers can have different numbers of these nodes. So these are the number of nodes of the nth layer, and this is the number of node of the n minus 1 layer. So the total number of parameters after doing all of this thing is just n squared. See, I have brought down something which was scaling as exponential to only a square of square scaling. I mean, that's a huge saving that I'm getting. Not only am I going to polynomial levels, I'm going at a very low dimensional polynomial. If I compare this with some of the normally used methods in quantum chemistry, so for a CIS, so configuration interaction singles, which basically means I have the ability to excite each of the electrons in the occupied space to the virtual space, the number of these configurations would be n squared. This is not the scaling of CIS. I'm just saying this is the number of configurations. So the number of configurations would be n squared. If I had CISD, so singles and doubles, these are commonly used quantum chemistry methods, that would be n to the power 4 scaling. And of course, as I showed before, if I had full CI, it would be n factorial or something to the power n, depending on whether you are, how you are counting the configurations. You can write it in both ways. Both ways will kill you just as quickly, so it's not a problem. I mean, it's not like one is better than the other. Okay, so we have indeed been able to get a huge saving in the number of parameters. Number of parameters for the full CI is factorial. Number of parameters here is n squared. Okay. So how do we do? I mean, we have reduced the scaling and all that, but do we even are we even able to get what we want? So using that, we have using this approach, this network construction, and our inputs are just the spins at each of the sites, and we will use different kinds of arrangement of sites. I'll show you. So if I try to train, you see that this training and validation is actually pretty smooth. It is pretty quick. So it seems that I can train these relative weights. Okay. After training, what is the error? Let's say I can train, but the errors are bad. That's not going to help me, right? So the errors you can see are not too bad. Most of the configurations, relative importance, I can predict within 0.01, and even the highest are not too much. The errors are not too much. So the model shows that there's low error for the CI coefficients that are predicted, which is great. More importantly, and this is something I will like you to note, so we have used some different kind of training than was done before. So this idea of fitting CI coefficient to a neural network was already achieved in 2018, but the errors were pretty bad. So the errors were of the order of 10 to the power minus 2. If the signed CI errors, all of them were of the order of 10 to the power minus 2, then the final energy errors would be horrible. And what we could really get is our root mean square error could be brought down to 10 to the power minus 6, minus 7, something like that. The reason we could do that is we separately trained the magnitude and the sign of the CI coefficient, because frankly speaking, in our scheme of things, we just want to understand what is the most important configurations. For that, we need the magnitude of the CI coefficients. We don't really care about the sign so much. So it it is not so important. Even if we did need the sign, we can train it separately and get back just as much accurate results. Furthermore, we have used a log scale to get the output because the log scale, see the configuration interaction, the coefficients can be very small or very large. So fitting that whole spectrum with one function becomes really complicated. But if you put it in a log scale, actually it makes much more sense. And this activation function, frankly speaking, we just tried quite a bunch, and this one showed good accuracy. So we used ReLU activation function. Okay, now let's look at the energy, because that makes more sense to a chemist or a physicist. Here is one more point. Okay, before I go into that, I should mention that this kind of errors that I showed before holds for a whole lot of systems: one-dimensional system, two-dimensional system, which was our reason for doing all of this, and for polyaromatic hydrocarbons that are one-dimensional as well as slightly two-dimensional. We haven't taken really big polynomials because our code is still not very optimized. But that doesn't, I mean, the idea, but we could show the idea very clearly, but we can't handle very large computation yet. Okay. Here in this plot, we take this system, which is a polyaromatic hydrocarbon, you can see, and we have plotted the energy versus how big a subspace we are taking. First thing that I will ask you to note is this is the energy of the training space. So we have taken a very small, like I mentioned before, a Monte Carlo sampling, small Monte Carlo sampling of states and their relative importance. From that, we have built a model and used that model to predict everything in the space. So it's like I'm modeling in a small corner of my Hilbert space and whether I can predict everything else in the Hilbert space and their relative importance. And it seems we can, because the variational energy as calculated using the model, our model ANN, is actually very close to the exact energy. The red one is the exact energy. So a model that was built in a very small subspace can be moved into a large, a rather full subspace. That was the main accomplishment of this work, I believe. And again, here we are showing that the same accuracy spans across one-dimensional sites, one-dimensional spin sites, tetracene, two-dimensional polyaromatic hydrocarbons, and a two-dimensional spin lattice. So all of these can be handled using this technique. So this technique is indeed quite versatile. That's what I want to mention. Now we come to the next step, which is, okay, so previously I had shown that I can rephrase a variational problem into a machine learning problem. There are benefits in that I don't have to calculate the operators anymore. I can just modulate the states and get away with it, so lower scaling. But what if I want to move from this CI expansion into a more matrix product state like ansatz? And in that ansatz, can I use machine learning? Because then I will have benefit of both. Benefit of MPS, which is lower scaling, and benefit of not variational problem, machine learning problem, because that has, again, lower scaling. So can I combine both of these lower scalings and still be able to get reasonable states? So for that, we can start with this MPS kind of a form. And what we can, how we can think about it is, if I multiply these two tensors, essentially you'll get this blob tensor, but this tensor also has just 4 legs, right? 2 legs due to these 2 sides and 2 bond dimensions that are sticking out. So now if I freeze the degrees of freedom, in other words, I freeze these matrix products, these matrices or these tensors, and just change the, or rather optimize the coefficients that pertain to this 4-dimensional object. So I basically have a more optimized 4-dimensional object. Now what I can do is I can do a singular value decomposition, go back here. So what will happen is these 2 will be updated. This 2 will be much better. I can again take these 2 now, So now I will have a blob over here. I can optimize this blob. I can bring it back, do this, and keep going like this. This is very similar to a two-dot DMRG algorithm for the ones who are used to DMRG, how we optimize a two-dot DMRG algorithm. And again, more important, I mean, beneficial from that two-dot DMRG algorithm is we don't need to compute the energy. So it's just these states we have to compute and optimize with respect to a final, some relative weight, which is our CI coefficients, signless CI coefficients. So using that, we have taken this system and we have tried to compute the we have trained and tested the matrix product states. So I will unpack this data over here. This is actually a bit complicated. So the dashed lines are the full CI expansions, ANN, but full CI expansions, as in the neural network trained full CI objects. And the bold lines are the ones that pertain to matrix product states that have been learned using machine learning. And the green pertains to testing and the red pertains to training. So you can see that our training, so this measure is such that if I reach 1 or I'm closer to 1, that is very good accuracy. And the further I am away from 1, its accuracy is lower and lower. So first thing I see that even with very small bond dimensions, as small as 20 bond dimension, I already have better accuracy than the full CI expansion using these matrix products. Both are machine learned. And it can go up to very high levels, almost as close as 0.9 or something like that, if I increase the bond dimension, which is what to be expected. You know, if you retain more and more states, of course, your accuracy will be higher and higher. Another thing, just to be honest, we have also plotted the time. So this is the time taken to fit the ANNCI, and this is the time that we are taking to fit our MPS. So you might think that, okay, we are getting good accuracy, but at a huge cost. But that's not quite true, because here I should mention that the ANN had those layers of kernel function, which I didn't talk too much about, but I mentioned that even in the hidden layer, there's some kind of a function that's applied on top of it to include some nonlinearity. So that actually takes care of some of the degrees of freedom. That's one thing. The other thing is, when we train this ANNCI, we are using some kind of a machine learning module, which are actually much better optimized than normally written MPS codes that we have in our labs. So given those two factors, actually this scaling is what I would expect. And we are working at reducing the scaling including parallelization and things like that. If I just look at the energies, you can see that the red and the black curve, they're falling on top of each other. So that is MPS, the comparison of MPS with M of 75 and the CI expansion. So you have to go to a bit higher to get correct energy accuracy. Yeah, but still this is possible. So we have been able to reduce the scaling. And why I keep talking about scaling and not the raw numbers is because scaling is what will help me to take it to really large systems. Let's say I have a patch of graphene, a two-dimensional, let's say 10 by 10 patch of a graphene. I mean, there's no way using full CI, even with artificial neural network, that I'll be able to train it. But with this MPS, there's a very good chance that I will be able to train it. That's one of the benefits. The other benefits is this extension of two-dimensional networks. So there are networks that have been proposed before us, of course, such as these projected entangled pair states, which are truly two-dimensional, and these cone tensor networks, which are actually very important for quantum chemistry applications, such as over here. So in these cases, you just don't have a simple matrix product state, but a complicated multiplication of tensors and matrices. But the necessity, the lack of need for calculating the energy actually benefits here also. So what has been proposed before is essentially variational approaches of optimizing these structures. But if we could transform these into machine learning approaches, which will again bring the benefit of machine learning into it, will actually will be able to extend things to two dimensionals. And just to tie it off, let me explain. So this is the FIMOCO complex, this protein, and there are seven iron atoms, 8 molybdenum atoms, and a bunch of sulfurs in between. So it's a horribly complicated system. Now you could think that I will put one orbital after another and extend it like in a DMRG. But the problem which will happen is, see, iron doesn't have just one orbital. All the d orbitals of iron and maybe even the 4s orbital of iron needs to be considered in our active space. So how will we arrange that? There's no good way to arrange that. The way that DMRG handles it is by increasing the M, by keeping more and more states, which makes it heavier and heavier. Instead of that, if we could actually reformulate it as a comb tensor, comb is like, comb that we use to brush our hair. So like that, if we take a comb tensor network, it will be much more computationally affordable, not scaling wise, but raw number wise. So with this, let me actually conclude. I hope to have shown you that there are ways of variational optimization of matrix product state, which gives a nice route to understand these strongly correlated systems. And of course, DMRG is one such very powerful route. It's almost routinely used these days extensively. And using those, we have been able to show that fused acene azulines, the system which had those azulines in the corner and acenes in between, has the largest decrease in singlet triplet gap, and even a possible singlet triplet crossover within a pretty small system size. And the reason for that also we could show using DMRG-like algorithms that is largely due to spin frustration. We have been able to extend these applications to two dimensions by leveraging neural networks and machine learning. And we have shown that ANNCI is a route to accurate variational energies. Finally, I really need to tell you this many times, that machine learning with matrix product state, it's like combining two very powerful approaches, and that is really being computationally quite efficient towards these physics-based model systems, or even molecular systems, as once we translate these comb tensor networks into machine learning forms. So that's what I have hoped to convey to you in the last 1 hour or so. And I cannot stop before acknowledging the people who were responsible in doing most of the work. So this is the group, a little bit old picture because we haven't been able to take a picture in the recent past. And the major work that I presented was by Madhumita and Shumanto. And Tonima and Mondira are also working in these projects, but they're pretty new. And funding from all these sources are greatly appreciated. And thank you all for listening at so late on a Friday. Thank you.
Thank you, Debashree, for wonderfully assimilating your work, which is a very huge and very good work to define it. So maybe we can have some questions. So anyone has any questions, so he or she can just unmute and ask. But before that, there was a question by Shaniur Rahman, that the question says that, ma'am, how do you manage to get the spin configurations?
We can take all, see, if I have two sides next to each other, each side, if it has two spins, of course, 4 sides would have all possible, like up, down, down, up, down, and down, up, all possible combinations. So that's one way. Now, if you have many, of course, you can create, again, all possible, only then the number will become really large and you will not be able to handle it efficiently. Does that answer the question?
Sunil, are you there? Okay. So, any more question from anyone? Yeah, so Manoj, you may please ask the question.
Hi. So you are saying that when you have polyacins, then it's trying to form biradical or diradical or polyradical things. Yeah. So is it really forming radical, or
it is not really forming radical, but it's going towards. I'll show you. I will explain that graph which I kind of zoomed through. 1 second. My presentation is still visible, right?
Yes.
Okay, so in the left hand side, you will see this is the occupation number. So here is the occupation number of each of the orbitals. Now, normally, what would I expect? I would expect that HOMO will be doubly occupied and the LUMO will be 0 occupied. Yes. But what you see is that the LUMO becomes, the HOMO becomes more and more closer to 1, and the LUMO also becomes more and more closer to 1, but it doesn't fully become 1, at least not between 12 acenes. And we have, of course, not done calculations bigger than this. So they're not fully diradicals, but you see what I mean. And also, more importantly, you'll see there are HOMO -1 also increases in occupancy, and LUMO +1 also reduces in occupancy. So it's not like just diradical is forming, it's like polyradical is forming.
Nice.
Okay.
So what about porphyrin kind of rings, ring-like structure? So do you
porphyrin, I haven't calculated, but the porphyrin will have less multi-reference, so it will be less diradical.
Okay.
The moment actually you incorporate nitrogen or things like that, what happens is, because they have a different level of that HOMO-LUMO, basically the multi-reference nature always goes down.
Okay, thank you.
Okay.
Next, Aniruddha has raised his hand. So, yeah.
Hello.
Hello.
Yeah, very nice stuff. Yeah. So I was asking about the 2D, the DMRG, the snake thing that you showed in one slide. So if I go from top to bottom in one direction, and in the from bottom to top in the opposite direction, then I can get the mist, the like 110 and those you showed. I can get those connections, right? But there will be a double mapping, I guess.
I will go back, but see, so the thing that I'm showing as this snake, it is essentially, see, then this is so I have to write my wave function somehow, okay, and then optimize the parameters with respect to the wave function, because I'm doing it variationally, let's say.
Yes.
So this one is like a matrix, or rather a vector, and this one is a matrix, this one is a matrix. So I can take this one. That will give me one full one full way of writing the wave function. Now, if I go like this, that will be another wave function. Now I have two wave functions. I cannot use both now.
Means kind of linear combination of means, is that wrong to say?
That's a reasonable idea. It's very difficult to pull off, because at each step, the way you are optimizing the
but I think here the combining will be doubly counted, because 1 and 2 again it will go back while it goes back.
So there will be double counting. So I have to remove all double countings. It will be a mess, in other words.
Yes.
It won't be so easy to optimize.
Yes. Yes. Yeah. Thank you. Yeah.
Okay. Any other question? So, Debashree, I have a question. Like all the molecules, or most of the molecules you have chosen, they have this conjugated double bonds. So, is it necessary to have?
Well, those are the ones that are most difficult to compute. If I remove some of those double bonds, much of these problems will go away. But in the same way, much of the the singlet triplet gap tuning, all of those will also go away. The reason why it takes a conjugated molecule is because there the excited states are in the visible range, and essentially if I'm looking for singlet fission material or any solar harvesting material, I would be targeting that range. So for that I need conjugation.
For the unconjugated molecule, do still can have this homo-LUMO separation very small?
Non-conjugated?
Huh?
Not so much, because sigma star will be much higher. Pi, I need to get pi star, and that too pretty.
Oh, that is the pi star.
Yeah.
Okay. So it is only the pi star that will come very small.
Yes.
So what is the typical, bond energy gap between this pi star when it is very close?
In our case, we have even seen systems which cross over. So basically, it can become even totally degenerate. You can think about it. But the relevant ones for singlet fission would be, I think, around 2 eV.
2 eV.
Around 2 eV. Yeah.
2 eV.
Because then the singlet triplet would be 1 eV. And that would be reasonable. As in, I'm looking at S0, S1 gap should be 2 eV, so that the solar radiation gets absorbed. And then what you get after singlet fission would be 1 eV. So that's the kind of numbers I have in mind.
And like this overlap between this HOMO and LUMO, they occur without any perturbation, or you have to perturb the molecule?
No perturbation. These are just molecules at 0 degree, nothing. If I incorporate perturbation, there will be even more interesting stuff.
Okay. Thank you.
Yeah.
Any more questions? Okay. So if there is no more question, let's thank Debashree for this wonderful talk, and keep visiting us.
Thank you so much. Yeah, I plan to. Okay, bye.
Okay, so we close the meeting with a thank to the speaker. Thank you very much. Thank you.